Hello everyone, welcome back to my Max channel. For today's video teaching, I will focus on the probability. So I will use the creative video teaching to explain to you what it means by tree diagram, multiplication rule, and also how to differentiate between dependent events and independent events. So have fun!
So for this example, we want to say a coin is tossed and then a dice is rolled, or a die is rolled. Now what is the probability that the coin shows heads and the die shows us a 4? Well, key thing to note about this example is you're saying and then, right? And then. Remember my intro video, I was like, there's the addition rule and the multiplication rule and. Well, note that this says and then. This is two separate trials. This is a coin is tossed, one trial, and then a die is rolled. So this is two trials. So the die is rolled is a second trial. Order doesn't matter so much, but the key thing to note here is that you have two trials. Okay, so a good way to do this, and a good way to concrete this maybe in your minds, is to just first draw this out as a tree diagram. So first let's say toss, which is like the toss of the coin. And so this is the first trial. We toss a coin, we can either get heads or we can get tails, right? And each of these happen with half probability, provided you're using a fair coin. And yeah, that's for our first event. But now, this is similar to how we did all those other in previous videos. We flipped a bunch of coins, we flipped them a bunch of different times, we had different trials going, right? This is the and then trial. Don't think of this as one trial, think of this as two trials. This is our second trial, is roll of the die. And roll a die, say we got heads, we got 6 rolls we can get. We get a 1, we get a 2, we get a 3, a 4, 5, a 6. 3, 4, 5, 6. Same thing, we get tails. We flip the coin, we get tails in the first flip, comes up tails. We can also get a 1, because we roll the dice afterwards. We flip it tails, and then we roll the die, we get a 1, we get a 2, we get a 3, we get a 4, we get a 5, and we get a 6. Now I'm not going to write out all the probabilities for each of these, just because that would take a little bit of time, but just note that each of these probabilities for the die rolls happen with probability 1/6. For all these branches, there's 1/6, there's 1/6, 1/6, 1/6, 1/6, 1/6, 1/6, 1/6, 1/6, 1/6. Alright, now let's kind of look at different combinations we can get of things. Let's think of all the different combinations for our sample space we can get. So say the first toss came up heads, because first a coin's tossed, then a die is rolled. The first toss comes up heads, and then for heads, what can we get? We can get a 1, a 2, a 3, a 4, 5, a 6 for the roll of the die. There's 6 sides of the die. So heads, and we get a 1. So now just respond to, we flip a coin, we get heads, and then we roll a 1. Or we could have gone heads and rolled a 2, then. Or we could have gone heads and then rolled a 3. Or we could have gotten heads and rolled a 4. Or heads and rolled a 5. Or we could have first flipped a heads and then rolled a 6. Exact same thing if we first flipped the coin and got tails. We could have flipped the coin, got tails first of all, and then rolled a 1. Or we could flip the coin, got tails, and then rolled a 2. Or flip the coin, got tails, and then rolled a 3. We could have got tails and rolled a 4, ooh, tails and rolled a 5, or tails and rolled a 6. Cool. Can you see any other sort of outcomes that could have occurred? No, I think we've covered everything. We've got all our outcomes kind of already accounted for. So now you'll note that in total we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 outcomes right here which correspond to our experiment. Our experiment is a two-trial experiment. Trial 1, trial 2. So yeah, this and then just refers to both of these happening together. You could even have 3 and thens and then throw a third trial in the experiment. But right now let's think about only 2 trials. Okay, so now we're going to find the probability that the coin shows a heads and the die shows a 4. So how many ways can this happen? How many ways can we get first a head and then the die showing a 4? Well, I mean, we could get a 4 here and a 4 here. We could have gotten the 4 right here, but that would mean we got a tails first. We want to first get a heads. Let's do red here. We want to first get a heads and then roll a 4. So this is the one event we can do. And this happens with probability 1/6. Okay, now note that on all of our outcomes, there's only one which has this. First we got a head and the die shows a 4. That's only this event right here. If there were 2 events, I would circle another event, but there's only one event. And that kind of makes things simple. If you say 1 event out of 12 is what we're looking for. So now let me ask you this. What is the probability that you flip a coin, first you get heads, and then the die shows 4? Well, you would say there are 12 events here, only one of them is what I want. 1 out of 12, right? So probability of 1 out of 12 that you get heads and a 4 shows up. Now looking at this here the same, I can also calculate the same way, right? Because the probability of heads and then getting a 4 on a die, we'll just write this as 4, that just equals probability of heads, probability of 4, given that you got heads, times probability of heads. You kind of see how this formula works here. This formula works in the way that first, I mean, it's a weird looking formula, and I bet when you first saw it, you're like, that doesn't make much sense, right? Like, why would I weight them like differently, like this? Well, you see, you first kind of say, okay, I'm going to get a heads. My first roll is going to be a heads. And you're saying, okay, given that I've got heads on my first roll, what is further the probability that I get a 4? So it's just doing the exact kind of same thing we did here. It's just the exact same thing we did on our tree diagrams when we counted branches of the trees. We would just say, okay, there's a half a chance I get a heads. So I'm just switching these two around. There's the probability of getting heads. And then we're timing that by the probability we get a 4 given that we got heads. You just follow the branch down, which is 1/6, right? So you're just following the branch, or just using our formula, which just follows the branch. It's the exact same thing. Probably 4, given that you got heads in the first row, times probably you got heads. And it also equals 1 out of 12. So either way you did it, perfectly fine. I'm sure there's also other couple ways to calculate. We found the probability that you get a head and the die shows a 4 is 1 out of 12. Alright, this question states that you have one card that's drawn from a standard deck of 52. The card is not replaced, right? So you got a deck of 52. Deck of 52, you draw one card. And then you look what it is, you say, okay, cool, I know what this card is. It's Queen of Hearts. Remember I was trying to draw that one beforehand? In a previous video, I was trying to draw the Queen of Hearts. Got it now, finally. And then you throw it away, throw that card away, and then you draw a second card. It's 4 of diamonds. Okay, so what we want to find is, well, first the event is that the first card's an ace, that's event A, and event B is the second card's an ace. So this is very common for multiplication rule things. You got first thing being something, second event being something. It's two separate things. So first we want to determine the probability that the first card is an ace. Then we want to calculate the probability that the second card is an ace. And then we got to see if the events are dependent or independent. And we want to find probability A and B. So a lot of stuff to do here, using both the T-diagram and the formula. You know what, I'm probably just going to start out by drawing a tree diagram. We got to do it in the end. It makes things a bit more simple. It kind of helps things be a bit more intuitive, I find. You got to draw something in math, always draw. It's the best. Okay, so let's say this is the first draw, which is the first card drawn. First card drawn. So now the first card being drawn, what are we looking for? We're not looking for all the 52 different branches, because that would take too long. Let's just separate this into two cases. Either the card is an ace or it's not an ace, right? So let's make our first event being an ace. And our second event is not an ace. Remember, this bar on top just means the complement. It means everything but an ace. It could be a 2, 3, 4, 5, 6, all the way to king. Well, how many aces are there in a deck of cards? There are 4. 4 aces in a deck of cards. The ace of clubs, the ace of diamonds, the ace of hearts, and ace of spades. And there are 52 cards in total. So probability that we draw an ace is 4 out of 52. And there are 48 other cards, so the probability you don't draw an ace is just 48 out of 52. Okay, so that's our first draw. And you know what? That's good enough information for us to do part A. What's the probability that the first card is an ace? Well, I only care about the first draw if I'm only calculating the first draw, so probably the first card is an ace is 4 out of 52. Sweet. Didn't even feel like we had to do any work for that at all. Can we do the second part? No, because the second part is for the second draw. Why don't we continue on this tree diagram for the second card. Okay, likewise for the second card, we'll only care if it's an ace or not an ace, because it's B is the second card is an ace. So let's kind of condition things on what happened for the first draw. The first draw, the first card could have been an ace, and then we could draw a second ace. Now, note that we're out of the addition rule. We're out of that thing where it's one event only and we're not worried about it. For multiplication rule, you always got a condition on what happened in the previous thing. Note here that that's not replaced. So, I got my deck of 52 cards. This is my deck of 52 cards. Let's say on the first draw I drew an ace. Let me find an ace here. Ace of spades. So the first draw, I get my ace of spades. And then I don't replace it, I just put it down. Can I slide it in here somewhere? Nope, I can't slide in there. I'll just put it down right here. Just right. Oh, just believe me, that is right down there. Okay, now I got my second draw. Looking through my other cards, how many cards do I have left? Well, since I already drew one, I've only got 51 cards left. And I'm looking for an ace. Well, there were 4 aces, but I drew one of those aces in the first draw. So my second draw, I've only got 3 more aces to look for. So if I were to get an ace on the second draw, the odds of that would be 3 out of 51. Right? There are 3 aces remaining, and there are 51 cards remaining. So out of those, so first it's 4 out of 52, but then the chance of drawing the next ace is 3 out of 51. Because I've already got rid of 1 ace and 1 card. Likewise for picking any other card out of the deck that's not an ace, considering my first card was the ace of spades. I've still only got 51 cards here, but I still have 48 other cards. 48 other cards which are not the ace, right? Because none of them got drawn in the first draw. So I have 48 other cards to draw from out of my 51 cards remaining. Because this card is already gone, this ace. Woo, get rid of it. Okay, now let's imagine that I didn't get an ace on the first draw. So let's put this ace of spades back in there and draw another card. It's the 4 of diamonds. Okay, considering that I drew the 4 diamonds, what are the odds I draw an ace? Well, I've still got my 4 aces remaining. So there's still four total outcomes, which give me success of getting the ace. And there are 51 cards remaining, because this 4 of diamonds is gone. So 52 minus 1, 51. And so it's a 4 divided by 51 is the chances that I get an ace. I still have my 4 aces in there. There's only 51 cards now. Slightly better chance of getting an ace considering I didn't draw an ace, which makes sense, right? If you keep drawing cards and they're not aces, you're going to keep getting more likelihood of getting an ace. Say I draw 30 cards and none of them are aces. Well, at that point, my next chance of getting aces is 4 over 22. It's a bit better chance. Getting an ace, right? And the chance of us not getting an ace, considering I didn't draw an ace the first thing, it's going to be 47 now. Because there are 47 other cards remaining. And this is also out of 51 because there's still 51 cards in the deck. Okay, so now let's look at this. What is the probability that the second card is an ace? Well, this is actually kind of tricky, but just think back to all the previous things we did with either rolling die or flipping coins, right? Because we'd always follow the branch to figure out what is the probability we want to find. And the second card being an ace can happen here, right here, or it could happen here. You actually have a condition on either you draw an ace in the first time or you don't draw an ace. So the second card as an ace is just this branch plus this branch. And for these questions like that, you always want to draw a tree diagram, or at least think of all your separate cases so you can not leave anything out. That's key. Okay, so this just equals 4 divided by 52, which is you draw an ace for the first card, and you just want to multiply that with you draw an ace for the second card. Your second card was an ace in that scenario. And that happens with probability 3 out of 51. So you gotta multiply those two probabilities together. Now this one here, same thing. For you don't get an ace for the first draw, which is 48 out of 52, quite high probability. But then the next one you do get an ace. So the second draw, you do get an ace. That happens with 4 out of 51. And so there you got the probability of you getting an ace on the second draw. Okay. Okay, so we found out all these things. Now I want to say, are events A and B dependent or independent? Let's go back to our definition of dependent and independent. For here it says events A and B are independent, then the knowledge that event A has occurred has no effect on the probability of B occurring. Right? So this just says, if I know that A has occurred, it doesn't change if B is going to occur or not. Is that the case for our example here? Well, not really, because if I draw an ace in the first card, it's totally affecting my probability if I'm going to get an ace in the second card, right? These two aren't the same. This here, for the second card, getting an ace, I have a 3 out of 51 chance. That's if I draw an ace for the first card. If I don't draw an ace for the first card, I've got a 4 out of 51 chance of drawing an ace for the second card. So if these events were independent, then this would have to equal this. But they don't equal, they're different. The chances that I get an ace, if I didn't draw an ace in the first, the chances I get an ace in the second draw, given that I didn't get an ace on the first draw, is actually a bit higher than the chances that I get an ace on the second draw, given that I did get an ace. So that was a big mouthful, a little convoluted. Don't worry too much about that, but just look at it, these aren't the same. So it really matters what I got on the first draw. What I got on the first draw affects my probabilities in the second draw. So are events A and B dependent or independent? They're very dependent. they are dependent events. Dependent just means it relies on one another, right? If you say someone's like, oh, you're really dependent, like, you depend on things. You depend on, I don't know, video games or whatever to play. Yeah, so this event affects that event affects, well, mainly the first event affects the second event very much. Just, as I was saying in the previous example, if I pull out cards, and say I keep pulling cards until I get an ace, but I pull out 48 cards, in my deck, and I haven't got a single ace. Well, the last 4 cards are all aces. So on that next draw, I'm going to pull out an ace. Those first 47 draws, or those first 48 draws, very much affect the probability of me getting another ace. Okay, so now, using this tree diagram and the formula, we want to calculate the probability of A and B. So, in this context, what are we thinking here? Probability of A and B. We want to think the probability of first, I get an ace on the first draw, and then I get an ace in the second draw. Which is actually just this branch right here. Right? First draw is an ace, second draw is an ace. So, we can just calculate that quite easy right here. A and B, I mean, just equals probability first you draw, first card you get, or I guess the first card is an ace, times probability the second card is an ace, given the first card's ace. Right? This probability just refers to that. Probability that the second card is an ace, given that the first card is an ace. And this just refers to probability that the first card is an ace. So that's kind of how the formula makes sense in terms of the tree diagram. We went over that before a little bit, but it's a very good thing to have concrete. So this, probably first ace, is just 4 out of 52. And that is just times this, which is 3 out of 51. Which I don't even actually remember what the answer is. It's something quite big. Alright, so I'm quickly going to note that this, 4 times 3 is 12. 52 times 51 is 2652. 2,652. And that just simplifies to 1 over 221. So, not a huge likelihood of getting both cards as aces, but small likeliness. And so that actually, the tree and the formula kind of are the same answer. You'll see that all mathematic concepts or all mathematic formulas have the concepts behind them. They always have some sort of, there is always some sort of drawing or picture, some sort of concrete idea behind everything. Alright, so this question says, a bag A contains 2 red balls and 3 green balls. Let's draw a bag A right now. First, let's make this red balls. Red. Okay. So, bag A, right here. Whoop. It's kind of my bag. Looks like a bag. Bag A. It has 2 red balls. 1, 2. And 3 green balls. 1, 2, 3. Alright, now bag B contains 1 red ball. Here's bag B. Very obscure abstract bags. They're actually art masterpieces. And so bag B contains 1 red ball and 4 green balls. Guess it's kind of Christmassy time, maybe. Right? You got the red and green together. It's kind of nice. Okay, so we got our 2 bags there. That's good for conceptual understanding. And now we roll a fair die. And if a 1 or 2 comes up, a ball is randomly selected from bag A. So let's say roll. If a 1 or 2 comes up, a ball is selected from bag A. If a 3, a 4, a 5, or a 6 comes up, 4, 5, or 6, a ball is selected from bag B. So actually, this is a 2-part experiment thing, right? Because here's our roll. Our roll is one thing, and here's our selection, our ball selection, I guess, from bags. Selection, and let's just make this a different color here, yellow, I guess. This is our roll right here, our roll phase. And we know our rolls happen with probability. A 1 or 2 happens probably 2 out of 6. And a 3, 4, 5, 6 happens probably 4 out of 6. Okay, so actually that makes, just using that simple information, drawing stuff that was a tree diagram, really helps things out quite a bit. You can really solve things quite a bit easier. So now I guess let's look at part A of the question. Part A just says, what is the probability of selecting a green ball from bag A? So here you're really just looking at bag A. You're saying, okay, I only want to select things from bag A. Well, how do I get to the part of selecting from bag A? Well, first I have to pick the die and roll a 1 or a 2. So first, no matter what, if I want to select from bag A, I have to roll a 1 or a 2. So, let's say green ball. So probably selecting a green ball from A, bag A. So first I have to roll a 1 or a 2, which happens with probability 2 out of 6. Then I have to select a green ball from bag A. And there are 3 green balls out of 5 balls in total. So I'm probably selecting green ball is just 3 out of 5. Simple enough, right? Oops. Do this again. 3 out of 5. So this just equals 6 out of 30. This equals 1 out of 5. Now, the good thing to note here is that this is the same thing as my formula. Remember my formula back from the first slide? We had here, probability of A and then B occurring can be calculated by first having the probability of A times the probability of B happening, given that A has happened. That was pretty general. Let's apply it to this example. Apply it to our last example over here. So now in this example, what would my A be? My A would be rolling a 1 or a 2. So probably that you roll a 1 or a 2. And the probability you select a green ball, given that you rolled a 1 or a 2, right? So it's probability of 1 or 2. And you times that probability with a green ball. Green ball, given that you got a 1 or 2 on your first roll. See? This here just corresponds to that, and this here just corresponds to that. That's why this formula works so well. That's what it gets it from. Alright, now let's move on to part B.
Hi guys, do you enjoy the video teaching? I really hope that my sharing do help you to have a better understanding of the concept of the probability. So till then, I shall see you in my next video teaching. Bye bye and have a nice day.